Hello and welcome back to Ganesh Institute. So in today's video, we are going to take up another topic from group theory, and that is modulo system. So what do we mean by modulo? Let's say I have n as a fixed positive integer and I've got another two integers a and b. Okay. So the modulo system says I need to write it in this manner. A is congruent. These three lines show congruent to B modulo n only if n divides A minus B. Okay, this is the symbol of division. So n divides A minus B. Then only we can say that A is congruent to B modulo n. What does it mean? Let's say if I write 5 is congruent to 3 modulo 2. Is it right? Because if you see, if I place here, n is 2, A is 5, B is 3. So, if you subtract 3 from 5, that is 2. And 2 divides n, that is 2, which is 1, right? So, this is the right thing. Or you can remember it in this manner that, see, if you divide 5 by 3, what will you get? 2 as remainder. This is the remainder. Okay. So this is also one way of remembering it. So we say the modulo system is like we have three integers. One integer is fixed and another two integers a and b are there. And we can write it as a modulo. A is congruent to b modulo n only if n divides a minus b. Got it? Now there are many types. For example, I can have addition modulo m. I can have multiplication modulo m. Okay, for example, if I say this, for example, if I write 8 plus 3 modulo 8, what it will give us as an answer? So see, this is 8, it's fine. What you have to do, just add them. 8 and 8 is 16, but this is modulo 3. Okay, so that means if you have to divide 3 by 16, 3 5s are 15, 1 is the remainder. So answer is 1. Getting my point? Okay, so what this addition modulo m says, if you have a and b as two integers and m is a fixed positive integer again, and you have addition modulo m, okay, addition modulo m, then you have to simply a plus b divided by m, and the answer will be the remainder. Okay, r is the least non-negative remainder when a plus b is divided by m. Got it? Just like we did it here. Now, when we have multiplication modulo m, similarly, you can apply the same fundamentals here. Multiplication modulo m, you have a and b, but here the multiplication modulo m will again give the remainder. Okay, so what we will do, for example, we have 4 multiplication modulo 3 5. Okay, so firstly operate 5 4s are 20 divided by modulo m, that is 3. So 3 6 are 18, 2 is the remainder, so answer is 2. Got it? So this is how you can use two modulo, addition, multiplication, and so on, whichever operation is given to you. Now, if I ask you to prove, you must have remembered this from the last video, that what do we mean by abelian group? What do we mean by abelian group? We have a group which follows, firstly, closure property, secondly, associative property, thirdly, existence of identity, fourthly, what? Existence of inverse, and the last bit is the commutativity, the commutative property. If a group if a set, non-empty set with any operation, that is, this is G, a non-empty set, and an operation is there, that is an algebraic structure, follows these 5 properties, then that structure is called as abelian group. Correct? Now I'm giving you a question as a blend of proving abelian group but using modulo system. So the question is, you are given with a set G. This is a finite set, so let me give you the elements also. 1 till 6. You have to show that this is a finite abelian group. Okay? That is, you have to show all those 5 properties, but the given condition is the group having order 6 with respect to multiplication modulo 7. Multiplication modulo 7. So what you can do, I would say that start with applying this first, then prove abelian group. So why it is order 6? Because the elements, the number of elements in the group are 6. Okay. So form a Calet table, or we can say composition table. You must have heard about it in the binary operation. So composition table. I'm making the composition table for modulo 7, okay? So this is it. I'm writing the members 1, 2, 3, 4, 5, 6. Similarly, 1, 2, 3, 4, 5, 6. And I'm having the operator as modulo 7. Okay. Now, what will happen if you apply all those properties which I just told you regarding multiplication modulo 7? What will you get? Okay. See, this is your first operation you apply between 2 elements, right? Binary operation. So this is first and first. The intersection will give you the answer here. So 1 multiply 1 modulo 7 into 1. So what will you do? Multiply. 1 ones are 1. If you divide by 7, you will get the remainder as 2 only. Okay, because we need the non-negative. I cannot do 7 ones are 7, then minus 5 is the remainder. I want a non-negative number. So I will leave it as it is, 2. Correct? I mean, so 1 ones are 1. I'm sorry. It has to be 1 ones are 1. So if you divide 7 by 1, I cannot do minus 6, right? I need to keep it 1 only. So let's do it 1. Have you got it? Okay. Now multiply. 2 ones are 2. But modulo 7. Divide by 7. You will get 2. 1 3s are 3. Divide by 7. Remainder is 3. 1 4s are 4. So it is, let me show you here again what you are doing. You have 1 modulo 7 4. So you will multiply. 4 ones are 4. You will divide it by 7. Okay. So as to get the remainder. The answer is remainder. Okay. No, non-negative remainder. So you cannot do 7 ones are 7. Correct. You cannot have negative number here. So you have to leave it at this step only. You cannot divide it further. So 4. 1 5s are 5. 1 6s are 6. Divide by 7 again. Similarly, you will get here same elements because it is also applying with 1 ones are 1, 2 ones are 2, 3 ones are 3, 4 ones are 4, 5 ones are 5, 6 ones are 6, right? Now, second row, second column. 2 2s are 4. 4 divides by 7, give you remainder as 4 only. 3 2s are 6. 6 divided by 7, 6. Correct? Then you have 4 2s are 8. Now, 8 can be divided by 7. 7 ones are 7. What's the remainder? 1. So, you will write 1 here. Then 5 2s are 10. If 10 is divided by 7, the remainder is 3. 6 2s are 12. If 12 is divided by 7, remainder is 5. Right? Similarly, 3 2s are 6. 6 is divided by 7, the remainder is 6 only. 3 3s are 9 is divided by 7, right? 3 3s are 9 is divided by 7, the remainder is 2. 4 3s are 12 is divided by 7, the remainder is 5. 5 3s are 15 divided by 7, the remainder is 8. It has to be 5 3s are 15. So you can divide it by 7 at 2 times. 7 2s are 14. So the remainder is 1. Okay. Then 6 3s are 18. And divide by 7. 7 2s are 14. The remainder is 4. Correct? Then you can have different numbers. 1 multiply by 4. 4 ones are 4. Remainder is 4. 2 multiply 4. 8 divide by 7. Remainder is 1. Correct? 3 multiply by 4. 4 is a 12. If divided by 7, if it gets divided by 7, the remainder is 5. 4 4s are 16. Divide by 7, you will get 2 as remainder. 7 2s are 14. 2 is the remainder. 5 4s are 20. If you divide by, just bear with me. So see what we are doing again. We are here, right? Here. So this intersection cell is this one and this one. So that is 5 modulo 7, 4. So 5 4s are 20. If it gets divided by 7, 7 2s are 14. The remainder is 6. 6 4s are 24. You have 24 next step. 7 3s are 21. What's the remainder? 3. Correct? Next, you have 1 and 5. You got 5. 5 2s are 10. The remainder is 3. 5 3s are 15. If 15 gets divided by 7, 7 2s are 14. The remainder is 1. 4 5s are 20. If 20 gets divided, you get the remainder as 6. Then 5 5s are 25. If you divide 7 by 25, it is 7 3s are 21. 4 is the remainder. 6 5s are 30. If you divide 30 by 7, 7 4s are 28. 2 is the remainder. Correct? Here. Next. This is 2 and this is 6. 6 2s are 12. If 12 is divided by 7, what's the remainder? 5. 6 3s are 18. 18 gets divided by 7. 7 2s are 14. 4 is the remainder. 4 times 6, 24. The remainder is 3. 5 6 are 30. 7 4s are 28. 2 is the remainder. 6 6 are 36. If you have 36, see it again. So 6 6 are 36 and you divide it by 7. 7 5s are 35. The remainder is 1. So we got our table here. Now I need to prove that the elements here and here, if operated by modulo 7, is that group an abelian group or not? So for abelian, what I need to check? Firstly, what closure property? And you know what this closure property means? If I'm taking A and B from the set, then the operation between them must be from the set only. So you have 1, 2, 3, 4, 5, 6 from the set, right? So 1, 2, 3, 4, 5, 6 from the set G. So all those when having this operation 1 by 1 or 1 by 2 or 2 by 6, 2 multiply operator 6, whatever the combination from the set, it should give you the elements from the set only. Is it the case from the table? Is there any result in this area which you could see and say that it is not from the set? Every number 1 2 3 4 5 6 6 5 2 4 3, any number, every number belongs to the group G. That means it is a closure. Okay, it shows closure property because we can see that all the entries in the composition table are from the set itself. Okay, so it is closed under multiplication modulo. Next property, associativity. So associative means what? If I take any of the numbers, okay, and the operation is multiplication modulo 7, if I operate them and change the order, firstly first two and last, and then last two, is the answer is same. So 1 multiplication modulo 2, what it will give you? 2 ones are 2, divide by 7, so the remainder is 2 only. Then multiplication modulo 7 3, so 3 to the 6. If 6 gets divided by 7, again the remainder is 6. So the answer for this bit is 6. Next up, what's the answer for right hand side? Okay, 1 multiplication modulo 7, 2 3s are 6. 2 3s are 6. Again, it will give you the remainder as 6. 6 ones are 6. It will again give you the, if you divide 6 by 7, again the remainder is 6. LHS is equals to RHS, because A star B star C is equals to A star B star C in the algebraic structure this. So it is associative. And anyways, remember this, whenever there is a modulo system, it always upholds associativity. Okay. Next, third property we have to check. What is it? Existence of identity. And what is identity? Basically, if I have an algebraic structure, a non-empty set, and an operator, binary operator, and I have considered any element from G, so whenever it is operated by this operator with a number and it gives me back the number itself, then I can call it as an identity, right? So which number is there in the table which is always giving me the number back? Tell me. See the table again. If I see 1, this is 1 multiplication modulo 1. It is giving me 1. 2 modulo 1. It is giving me 2. 3 modulo 7 1. Giving me 3. 4 modulo 7 1. Giving me 4. 5 modulo 7 1. 5. The number itself I am getting, right? If I do it by 1. If I do it by 1, so 1 is the identity element. Again, see from this side. If I keep this element constant and change rest of them, 1 multiply modulo 7, 1. It is 1. 1 multiplication modulo 2. This is 2. 3, 4, 5, 6. I'm getting all the time these elements. So that means whenever I'm having any number and I operate it, and here the operation is multiplication modulo 7 with 1, I'm getting the number itself, correct? So 1 is my identity. Okay, so existence of identity is there. And fourth property is existence of inverse, correct? Existence of inverse. And inverse says whenever you take the element again from the non-empty set and you apply this operator with the inverse, then it should give you the identity back. So that means if I place the value, any element from the set 1, 2, 3, 4, 5, 6, any element, if you take and you apply this operator, multiplication modulo, which number is there which is giving me 1 back? Okay, which is giving me 1 back. Okay, tell me. I'm taking 1 by 1 all the numbers. 1 time 1, 2, 3. And I'm having multiplication modulo 7, multiplication modulo 7, multiplication modulo 7. Which number will give me identity, that is 1 back? Tell me. What should I place here so as to get this number identity element? Tell me. So if I have 1, if I multiply it by 1, 1 ones are 1, I'll get 1. Yes. What is there? This is 2. Which number has to be multiplied so as to get 1? Which number is multiplied by 2? It is 4. 2 4s are 8. If you divide it by 7, you will get 1. Correct? What should be multiplied by 3 to get 1? Tell me. So at the place of 3, 5 3s are 15. 7 2s are 14. It is giving me 1. Correct? So that means from the table, every number, see, here is the identity element. Here is the identity element. Here is the identity element, identity element, identity element, identity. Every single row or column has their identity element. So for 1, the inverse is 1 because it is giving me identity element. Correct? For 2, the inverse is 4 because it is giving me identity element when gets operated under addition, multiplication modulo 7. For 3, the inverse is 5 or vice versa. For 5, it is 3. For 4, it is 2. For 6, it is 6. Okay? So every number has got their inverse. Correct? So that means, yes, inverse exists. Now the last property, which is commutative. Remember, if I give you a throwback, we were supposed to show in this question that this particular given group of elements 1, 2, 3, 4, 5, 6 is an abelian group under operation modulo 7. So firstly, we found out all the elements in the group under modulo 7 by creating a table. And now to check whether it is an abelian group or not, we are confirming with those 5 properties: closure, associative, existence of identity, existence of inverse, and commutativity, right? So now for commutative, what is it? If I'm having 1 modulo 7 into 1 or 2, it should be equal to 2 multiplication modulo 7 1. Because for commutativity, what is the condition? If G star is the algebraic structure, then A star B is equal to B star A, then only we can call it what? Commutative. Correct? So let's see. 2 ones are 2. If you divide it by 7, you will get the remainder as 2 only. 2 ones are 2. Again, this is always commutative because we are using multiplication, and multiplication is commutative. So hence we can say, because all the 5 properties are proved, this is an abelian group. Hope you have got the modulo system and as well as the revision of abelian system, abelian group. If you like this video, then don't forget to like, share and subscribe my channel. Till my next video, take care of yourself. Bye-bye.